Welcome back. In today's video, we are exploring spherical coils. First, we will parameterize the coil using Plotly library, and then we will analyze and visualize its 3D magnetic field using Magpylib library. And then we will jump to Fusion 360 to design a 3D printable holder. So here we are in Jupyter Notebook, and let's start by importing the necessary libraries, and then we will define our initial parameters, again in SL units, and then we move on to the function which creates the spherical coil. From previous videos you'll see similar logic of dealing with layers. So again, for each layer we are creating a separate layer coordinates and then a separate Magpy current polyline object, and then we are using Magpy collection function to append all of those coils together, and we are also returning the full coordinates. And also for better accuracy, here I added top lead and bottom lead, which we will see in the visualization. However, the main difference this time is how we handle the parametrization, and there is a small but crucial detail I want to highlight. So there are two ways to parameterize a sphere. First is using a uniform Z step, and the second is using uniform polar angle step. To show you exactly how they differ and why it matters, I'll set up a separate Jupyter Notebook for us to explore. So again, let's import the libraries. So how is the sphere defined mathematically, or how it's parameterized mathematically? It's by using polar and azimuthal angles. So here the phi is the polar angle and the theta is the azimuthal angle. So here we see Cartesian coordinates of x, y, z. And let's define our initial parameters, and n is the number of turns. So azimuthal angle is the same for both cases. It starts from 0 and then it goes to 2 pi for each rotation, but because we have n turns, it goes from 0 to 2 pi multiplied by n, and t is just a parameterization value which goes from 0 to 1 uniformly. Here is the t. So theta as a function of t is 2 pi n t. This is that thing implemented in the code. So let's run this. So first method is the uniform polar angle, where the polar angle goes from 0, which is the north pole, to pi, which is the south pole, in uniform angular steps. So it goes from 0 to pi, this pi, in uniform steps. That's why the function of t is pi times t. So here we define phi as pi times t, and here we have conversion of Cartesian coordinates. In second method, we want uniform z spacing, which you'll see better in the visualization. In this case, the z goes from r, which is the radius, to minus r in uniform physical steps. So when t is 0, z is equal to r. When t is 1, z is minus r. Then we can derive this formula that z as a function of t is r times 1 minus 2t, where r is the radius. And then when we substitute this original equation back, where we found that z is r times cosine phi, we get that cosine phi of t is 1 minus 2t, and to find phi of t we take arc cosine of this, and we get that phi of t is arc cosine 1 minus 2t. So here is that implementation. So let's run this and visualize them using Plotly library. So here we see the difference for 5 turns. This is uniform polar angle and this is uniform z. As you can see, in uniform polar angle we have more dense windings in the top and sparse winding near the equator. In uniform z, the winding step is equal in z direction. It may seem a subtle difference, but when it comes to magnetic field homogeneity, we'll prefer uniform z parametrization because this gives more homogeneous field. So now, after we understood why we prefer uniform z winding and why we define phi as r cosine 1 minus 2t, let's just run this function as well. And then the rest of cost function and visualization in 3D is the same as in solenoid and Helmholtz coil videos. So I'll just run them here. Now let's create the coil using our functions, which we just defined. So coils is the Magpy object, and coordinates is the list of coordinates, which is NumPy array. And the grid is a 3D array of points where we are interested in magnetic field. So let's run this as well. So here we see the visualization of our coil. As we defined earlier, we had 3 layers. Here we can see that they are parameterized correctly, and we see layers as expected. And now we can see the results in 3D by running visualize 3D function. And here we see the field, which is as expected from the right hand rule. We can disable the sphere and see that field points up quite uniformly, which means that the field inside is homogeneous. And the quantitative description of homogeneity is given here, and the field strength is given here. Another way to visualize the coil using the native Magpy show function, we can just call show from Magpy object coils and assign browser to render. So I will run this, and we can see that we get a similar result. Here, this is just easy way to make sure that the current runs in the correct direction and everything is correct in the layers as well. So this is a easier method than Plotly library, but Plotly is more robust for visualizing individual vectors of the field. So once we are done here, we can export the CSV file of the coil in order to create the 3D printable holder for the coil. And to make the coordinates easier, because we only need a single layer, we can just rerun the functions using only one layer. So I will disable plotting for now, and I will run them again. And now I will save my coordinates in coordinates.csv file, which I will later import to Fusion 360 and use them to create my holder around it. So now we are in Fusion 360, and first thing we need to do is to enable importing CSV file. For that I will use an add-on, which is located in Utilities, Add-ins, Scripts and Add-on. And the link to download the add-on will be in the description below. So here I enable import CSV. One important thing here is to pay attention to units, which by default is millimeter. But we need to remember that for Magpylib, we defined all of our units in SL units, which is meter. That's why I will select meter here. Otherwise, the coil would be really small. The style, I will leave lines because I want my points to be connected via line. Otherwise, I can select points, but I don't want that because it will leave them as individual points. So I press OK, and then I import my CSV file. Okay, here we see our coil. So what's our strategy is to use the coil's CSV coordinates as a path, and we will draw a rectangular box which will simulate the multiple layers we will add based on the dimensions of the wire, more specifically the diameter of the wire. And then we will use that rectangle as a profile to sweep around this path. And then we will create a sphere, which is the holder, and then we will extract the path from the sphere and we'll be left with the holder. So to start, let's select YZ plane to draw a sketch of the profile. Okay, here we see the endpoints, and I can zoom to the bottom endpoint. Doesn't matter, we can start from the top, but I prefer the bottom part. And I draw a rectangle here, which will be the cross section of wires. So the width of the rectangle is 1 millimeter. The length, let's put 15, assuming we are making a holder for potentially adding 15 layers. Then I want my profile to extend from the bottom point towards bottom. That's why I will select this and the point, and this dimension would be half of the diameter, which will be 0.5 millimeter. Also, I want to center my rectangle around the wire. That's why I will select this and this. This would be half millimeter as well. So when you see black, I can use pen here. When you see the outline turning black, it means that the rectangle is fully defined. Another tip is to use this home button, which gives us overview of 3D. So I can just finish my sketch here. Then I will go to create, sweep, and I will select the profile, the rectangle which we just created, and the path, the CSV parts. So now we need to create the outer sphere. For that, I'll go to create, sphere, and to select the origin, I will just orbit around to make sure I see the origin. Now we see the preview of the sphere, but we need to make sure that the operation is not cut, but it's a new body. And 100 millimeter diameter is okay because we want the outer edge to extend beyond the sphere, so then we can cut this. So this is okay, that's why I'll press enter. Now we need to do Boolean operation and cut the trace from the sphere. For that, I'll go to combine. Target body, I will select the sphere. No, target body is the sphere. And the tool body is the trace. And I select cut as an operation. Here we see the preview and I press OK. Okay, now we see the sphere cutted. And now we are left with the trace holder. But now we are not done yet. Why? Because to print this, first we need to hollow it, and also we need to cut it in half and make pins to connect. So first of all, let's create the inner sphere to hollow our structure. For that, I will disable the view of body 3. I will create a new sphere around the origin, and the diameter would be 70 because we want it to be smaller than the radius of initial coil, which was 40. So okay, now I will enable both, and I will do again Boolean, this time cutting the body 4 from body 3. To make sure that the cut was done correctly, we can go to inspect and see cross section. We can select this plane, and now we can see that the sphere is hollow. This would save a lot of material while printing, and also we'll need the inner part to be hollow to house the RF coils as well. To disable the cross-section view, we can just go to analysis and disable this. Now we are back to our sphere. To cut the model in half, we can use split body. The body is body 3, and splitting tool is the plane. We will use YZ plane. So now we see the preview, and I can press OK. And now we see the model split it into body 3 and body 5. So again, here we see the cuts. So what I want to do is to create a extrude here, which will be our pins, and then I will remove those pin locations from inner parts here so they can attach each other. Now I will repeat the Boolean operation again. So the target is second one, and the tool is the body 3, and I want to keep the tool. Let's look again. Okay, now we see that nothing was damaged. But one final consideration is here, the pins will just go into each other with zero margin. To create the margin, I will do offset face and select this pin. And let's do 1 millimeter. We see it shrinks. To avoid shrinking, we can just do -1 millimeter, so it expands. I'll press OK, and I will repeat the same. Now we can see that the top pin, let's say housing, or the mate got bigger. So we can repeat that for here. To do final check, let's use move function to move our body free a bit backward. And here we can see the margin we created. So now we can see that we have some tolerances left for the 3D printer, which is what we desire to do so. And this was it for today. Thank you very much for your attention.